Thank you very much for inviting me here, because we met actually over dinner, must have been, what, 6 months ago or so, something like this, and it just all fell into place finally to have both Mark Edwards and Francesca Morgante, who invited me to do the same kind of a thing, clinic and whatnot in London, and then from there to see both of you, Tim and Richard, here. And the idea was to be able to present a sort of a vignette of a bunch of things that we're doing. And there's lots of other things that are going on in the lab that we're not going to necessarily talk about, but please feel free if you've had an opportunity to look at some of our papers. The idea behind this is that technology in movement disorders is not a new thing, and we use technology quite effectively. For example, deep brain stimulation, where primate work, electrophysiology and recordings that we do in the operating room, externalization of electrodes that we do in our lab, and as you'll see, Robert Chen in Toronto doing this, small number of people, but certainly using some form of technology for treatment. MR localization, for example, and all the work that has been done in terms of localization of electrodes. All of this is technology. Building of the implantable pulse generators, from pacemakers in cardiology to now in neurology, duodopa, pump therapy, PEG-J tubing itself to be able to sit there for years in the small bowel. All of this is tech. It may not be something that physicians are directly involved in building and making. This is an engineering thing, but more and more we're seeing the ability to have clinicians guide the development of this technology, including, for example, the duodopa pump. We've been working with AbbVie to try and get a pump that allows you to program that pump to the phenotype of the patient. So, because right now it's a standard pump that is going on at the same rate, but patient might be off more, on more in the afternoon, and that device doesn't actually detect and do that. So that's the next generation of closed-loop pump therapies. Apomorphine pump might be amenable to the same kind of thing. Gamma knife, radiofrequency surgery, now this MR-guided focused ultrasound. Again, all technology that is being used for treatment in movement disorder world, not necessarily with assessment like PET and DAT, and we talked about the significant limitations of those technologies there. EMG and ultrasound we've developed, which we'll talk about, a technology to be able to optimize injection of botulinum toxin. The problem is most of these are expensive technologies. They're often not accessible to for a variety of reasons, and I was talking about this at dinner yesterday. We've got in Ontario about 45,000 estimated patients with Parkinson disease. So our province of Ontario is about 15 million, which is about, what, 3 times the size of Ireland. In my area, where I am in London, Ontario, we have about a 3.5 million catchment for me. And there's only really 2 movement disorder people, myself and one of my former, now 15 years ago, fellows, and she largely does clinical medicine alone, and that's it. So in clinical practice, for example, I have over 4,000 Parkinson's patients in my practice, about 500 dystonia patients, a huge clinical load that is there. How are we going to be able to address this clinical load in terms of being able to provide assessment and care? The geography is large. When I go home, my drive from Toronto Airport to my home is 220 kilometers, which is really next door. It really is for us. And I used to go to a place called Thunder Bay, which is a 2.5-hour flight. And there's no neurology in Thunder Bay for a population of 300,000. Well, here are all these people scattered in a country like Canada where near distance is 500K. How are we going to be able to assess and provide care, let alone populations that are even north of us in Yukon and Northern Territories? So the need for us to have the experts brought to the local area has been great and has always been. Telemedicine is not really able to do this very well. So the idea was to bring the expert to the community using whatever technology has been available. The problem is, over the years, the technology, or many years ago, the technology was not modern enough. And we were chatting about this, Richard and I, that in the days at MIT when we would have 1 megabyte of data was huge. What a lot of data. When I brought all my animal data back from Boston to do the next level of computation to London, Ontario, I had 10 disks of 10 megabytes, or 100 megabytes of data. And that was treasure. I guarded that 100 megabytes. 100 megabytes, now that's 100 megabytes. That's how trivial that data is. So we have matured to the point of having technology now to be able to be good enough to be able to do what we want to do, which is portable, reusable, cheap by volume, yet high fidelity. Because one of the things that, and again, we talked about this briefly, I don't want to have a system that reduces the number of sensors or assessments and whatnot to just one, so that all you're getting is a global measure. It's great if it has the fidelity to give you all of the things that you want. But you don't want to have a system that provides you mediocre information, because your outcome will be mediocre. You'll be still at the diary and UPDRS level, right? So the idea is to still have fidelity in the system to target what you want to do with that information, right? So two things that we wanted to do is, one, develop an assessment technology suited to what you want to do, and yet have it attached to a therapeutic that you could either repurpose from existing technology or treatments, or apply in a way that optimizes them. So that was really the idea. Right? So let's start with objective measurement of motor symptoms in Parkinson's disease. As we know, there's tremendous intra and inter-rater variability in clinical assessment. You need to have a huge amount of expertise to be able to do assessment. For example, in dystonia. In the clinical world, I teach this. There are 3 of us in Canada that have done as much Botox as we have: Joseph Choi in Vancouver, Earl Konsky, and me. And 25,000 injections, so large volume. So what do we do in terms of our assessment? Well, I look at somebody like this, and I look at them like that. I call that the cervical dystonia dance that we do around this person, and say, I'm going to inject 25 units in the right SCM and 44 units in this. This is all bullshit, right? Because we're just making stuff up, largely, whether it's DBS or whatever. Now, I happen to get it right, well, because I'm the boss, so I get it right. But other than that, the fellows, even though we have a lot of patients, are not able to learn how to do this injection, because they've got to inject what I say. Because the patient is not going to say, well, sure, why don't we let Dr. Sharma try this? And, you know, if my neck falls off and I can't swallow for a week or 2, that's all right. I mean, it's not a problem. No, 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 no. They're going to trust my magic hands. Well, the magic hands are all ad hoc. There's no actual ability for me to carry that over to the next patient. It's somewhere, but I can't translate it to somebody else. I can't teach you. That's the reason why we've tried. It's not easy to do, right? So all of this in Parkinson's disease is the same. So we started years ago by reporting on the necessity to use technology. And again, as you say, some of these are in technical journals, some of them are in the clinical journals, depending on, and we sort of fall in between some of these. So the first paper was this, capturing whole body mobility of patients using these inertial motion sensors, or what we call IMUs, the challenges and what. So we validated a whole set of IMUs. There was some loud sound. Did you hear that? No, no. Right. It must have been the microphone I tapped. And then the second, ecological, so whole body kinematics in the ecological environment, which is actually in the patient's home environment. Why? Because many of us know that when you come to the lab, it is not possible for you to have the environments that patients are facing at home. So one of my patients regularly tells me that when he walks from his deck onto the lawn, that's when he freezes. Well, I ain't got no lawn in my lab. Right? So it's not possible for us to simulate that environment. Now, we did some of this work in virtual reality environments, and we were talking about it briefly yesterday and today, where we had a system, and this was many years ago, 10 years ago. Those papers I'm not presenting. We put these patients in a VR apartment. Right? So we built a 2-bedroom apartment, and we had these people navigate. And Parkinson's patients got completely lost. They had no idea as to how to navigate. There was no strategy as to saying that I want to go from that bedroom into the kitchen. And it went from this bedroom to that bedroom, back again this bedroom, went to the study. So, oh, that's a toilet, that's not kitchen, and like that kind of thing. Whereas controls had a strategy as to what. So the idea behind this is that you want to be able to take tech home or simulate that environment within a system, which we're not going to talk about today in the VR domain, so that we can see what is happening in an ecologically valid scenario and assess them in that environment. Those days, we had no way to take this tech home to the patient, so we brought the VR world. But VR has its own problems. You have to get used to the VR world, and people felt that it wasn't real, and even VR domains were not good at that time. So we started there. And then in our mind, we divided this into saying, wait a minute, there's a global component of this, but there's also a regional component. So we divided this into what we call local measurements, where, and I'll talk about a little bit about that, and then a global measurement, where you want to measure all of these motor symptoms of Parkinson's disease: tremor, bradykinesia, discriminatory, gait, et cetera, et cetera. The first one you can measure in the laboratory. The second one, you want to measure them all together. You want to not just measure tremor at the expense of gait, or gait on a gait carpet at the expense of the upper body. You have to be able to measure all of them together. Why? Because a patient with Parkinson's disease can have dyskinesia in this arm but tremor in this arm. They're walking like this. You're not going to be able to have a kinetograph on one arm measuring tremor but not on the other side. With tremor, the idea came about based on work that we were doing in biomechanics of arm motion. We had sensors that we were using. What we were finding was that there was a lot of bleed over. What does that mean? That means wrist motion was contaminating, elbow motion was contaminating, shoulder motion. Couldn't tell what was happening at which joint because we were just using accelerometers. Accelerometer is not good because if I have a motion like this, if I have a motion like this, or if I have a motion like this, the oscillation looked virtually the same. I couldn't tell whether the tremor was coming. I could guess, but I couldn't tell that it was coming from. And then on top of that, the additional degrees of freedom of lateral movement, flexion, extension versus rotation, all of this thing happening at the same time. This is extremely difficult visually. As Richard mentioned, the other leg is in the clinic, and in the clinic, I'm trying to treat patients with tremor. We have no treatment for essential tremor that is good. You've got DBS surgery, which causes their speech to go away and can't think after that and all these kind of things. And you've got all these oral medicines when 17, 80-year-olds, causes cognitive problems, hypotension, bradycardia, nothing really available to treat them. Parkinson's disease is the same. Levodopa responsivity is not great with levodopa, with Parkinson's disease. So botulinum toxin had been tried many, many, many years ago to try and treat tremor by injection of Botox to dampen the activity of the muscles. However, the problem remained that you couldn't tell, like the cervical dystonia dance that I did, which joint was affected and to what percentage, and then which muscles contributed to that. And toxin injection requires you to precisely measure that dynamic before you are able to inject those muscles. So we decided that this technology that we were using for arm motion was not good enough, and we moved to another set of sensors, which are essentially torsiometers and goniometers and torsiometers. And the idea behind these was that one sensor, and we found these after a tremendous amount of looking and making modifications to the hardware from this company, which they did for us, thankfully, that these sensors are agnostic to the joint, which meant that this sensor would pick up rotation, but it wouldn't pick up flexion extension of the elbow because of torsion, and we placed them in a particular way. All of this has been published, as I'll show you, in 4 locations, and it was beautiful. We were able to, it took 2 years of work, but we managed to get to a point where all the code was written to isolate that, and this was the first little thing which was in that left is a media picture. The right is a patient with young onset Parkinson disease, and he was treated with botulinum toxin. Was one of her early patients, and the bottom video is playing. So absolutely remarkable benefit. Right? Now we've done hundreds, and I actually inject a lot of people. In fact, I don't do any physical examinations of tremor in these patients in my clinic at all. Olivia Samotas, who is the young lady there, who also had done all the spinal cord work, was doing her master's at that time with me. These are the sensors. I'll have another picture of it in a second. I basically see the patient in clinic, say, you've got bad essential tremor. I send it off to the lab, and we're the only ones in the world that actually have it, so I only provide the service to, well, me. And so, so the patient gets this assessment done. The assessment of tremor is correlated with an AI algorithm that we've developed now that we've got hundreds of injection cycles to pick the muscles and give the dose. So she gives me a sheet which says FCR 10 units, FCU 5 units, left side, pronator teres 25 units, pronator quadratus 5 units, leave out this, and that, and I inject them. And so she does this thing, gives me the sheets, I go to clinic and I inject them, or the fellows inject them. And we've now done hundreds of these patients, published a lot of data on this, many papers. Here are the sensors. These are totally wireless, yeah? So this is the torsiometer built in, and the goniometer. This is a wireless transmitter, and it's placed like that. It could be the other way, it doesn't matter. And there's 4 of them. And so there are 4 of them like this, and they will transmit to a little laptop automatically. And sure enough, you get, and both arms can be done simultaneously. The reason for that, of course, is that the tremor in the 2 arms can be quite different, as we know. Essential tremor is certainly not rhythmic, as we were talking about before. It is asymmetric. So in fact, just like dystonia, you will have a tremor that goes like this, or you'll have a tremor that comes to the midline. It is not like this. We've published a couple of papers on the biomechanics of this in the Canadian Journal, looking at in fact, trying to, I suppose, in a way, validate Kailash's thought or other people's thought that this is a dystonia, all of it, and not really tremor or whatever. Who cares? It's some sort of a label that you put on. For sensors, it doesn't matter. It's just motion, right? And that's the important thing, because you call it tremor, you could call it coffee. It doesn't matter to the machine, right? So you could detect chorea with this. There's no problem detecting anything else that you have as a hyperkinetic state. If it's hypokinetic, this sensor won't detect it because it's static, right? And so this is the old wireless system, and I showed you the new one is totally wireless. And we've published a series of papers, a couple of them in PLOS One and other places like this. I don't remember now where they are. But over the years, 2015, 16, 17, 19, and I think that this is an old study. The PD one is published now. I can't remember where. Sorry. And you can see that in both PD and ET, there's a remarkable improvement in quality of life. And these people are now coming back. Initially, of course, like in spinal cord, some people say, oh, well, we're placebo response. I mean, if you can drink your cup of coffee, why would you want it to be a placebo response? Certainly not at 5 years, right? And so that's great. If you have a placebo response, why not? Interestingly, the tremor actually reduces over time. So people are now in what we would call an open label phase. So they were coming every 3 months as part of our protocol, and now it's on demand. So they call at 6 months saying that, oh, I think it's bad again, can I come in? Right? And the advantage of this is that we've been able to keep in the Parkinson's patients levodopa dose much lower than what I would have expected. And there are people that are still on monotherapy toxin for their PD, right? In terms of other symptoms not requiring levodopa, tremor being the most dominant. So I actually offer tremor treatment, Botox treatment. This is actually Xeomin that we use, the Merz product. Botox is just rolls off your tongue in a way, so it's wrong. But anyway, Xeomin, the Merz has done an RCT using our system, and that's right now under review in movement disorders. And they're planning a phase 2-3 study. Well, actually, it's been planned. It's been done. It'll hopefully be starting next year in March, April, that kind of a timeline, right? And they're using the sensor technology to quantify. Funnily enough, in the study that's under review, 6 investigators in Canada and the US were involved, and all of the David Simpson and these guys all insisted, well, the clinician must have final say over this. And I said, well, that's fine. I mean, if your eyeballs are better than the machine, please go ahead. And so we allowed them freedom to select their clinical judgment. Not a single one did. Nobody used their clinical judgment. They all used the output of the system. And the system is built so that the recording is output to cloud. Software runs on cloud, automatically analyzes the data on cloud, and gives you the readout. So you just get a readout as a physician. All you've got to do is put the sensors on, go on to the side, analyze. You don't even need to analyze it on your laptop.
I mean, compare this with dental or surface electrode, so surface EMG, because you would use that for like neuro tremor and injecting.
I don't like EMG because it doesn't allow you to quantify which muscles it might be coming from, right? Because you need angular deviation to know that this is so much supinator, so much, because they're actually co-contracting together. And you can't tell that this is so much is rotational, and hence it must be coming from PQ and supinator, pronator teres, that kind of a thing, or bicep. So with EMG, it's a compound movement, right? And so we've got simultaneous movement like this. We have not compared it. We're not
surface electrode, so if you record the muscle activity and then...
I don't think that you can actually isolate the muscle. How are you going to get to supinator and teres, and those muscles are too deep. Quadratus is so deep. And pronator quadratus is a huge contributor. Huge contributor. For Richard, I didn't say this in London, for one of my graduate students in engineering, Yokesh, has built a full-size biomechanical model now of individual muscles. There's some software that allows you to do this, actually put in all of the muscles, in all of the muscles of the upper limb, and has been now able to build this model to say what percentage of contribution is coming from which muscle. So that's finished, and that's the first paper he's writing right now, along with Rajni Patel, who's the head of our advanced robotics group in the team. And then the next phase of it, which he's doing, is we've got literally 1,000 patients worth of data. One of the other groups actually in Ottawa has a paper coming out in Nature Reports, accepted last week, on a computational model using, and I can send you that paper actually, the draft of it, or the accepted proof of it, looking at how the machine now intelligently parses. We do this sort of in a pseudo AI way currently, 50-50, so supinator, pronator, and I don't really know how much pronator teres is contributing versus quadratus to that rotation. I just divided 50-50, but it's incorrect, right? So what Yokesh has done is that he's built this model now saying that actually 30%, 30% is coming from pronator teres and 70 is from quadratus. You can imagine now if I decide to put in 25 units, 50 units, I can divide it now appropriately to this. So when he finishes in the next 6 months, the tremor data that we've collected, kinematics, and puts it on this model, the hope is that he'll be able to tell us exactly how to separate that dose. So now, right now, when Olivia does give me that printout, it is sort of an arithmetic algorithm rather than a computational algorithm. We say it is because it sounds more intelligent, but it isn't actually. It is more experiential. That's what we ended up doing in the patients, but that's not really a true computational model. Yokesh is going to build that, finishing that hopefully in the next 6 months. So this will be a completely smart application. Anybody that's a tech can put this on, get the tremor, and you can put it in any position once you zero it, and then it'll give you the readout, right? When I presented this in Italy about 1.5 years ago, I literally had physicians come up to me and said that, well, you're going to you're replacing physician expertise. This is wrong. What do you think we're going to do? So we said, well, hopefully something better than guessing what's happening with the tremor, right? And so there's a lot of pushback in terms of even including Mertz, who in their current phase 3 study don't want to use tech because somehow the clinician's eyeballs. This is so wrong. I mean, it's just incorrect. That patients are, we know from all those old studies that you'll get weakness. You'll not dose properly, right? And this is something precision that you need to do. So that's tremor tech, okay, very briefly. Whole body measurements in Parkinson's disease was our next challenge to say that, you know, yeah, we all have, not all have, but those of us that have done gait things, you know, we've got a variety of different of these camera type things that are in the labs, but they're not portable. You can't take them anywhere. There is high precision, and you can assess multiple things at the same time from the camera. But again, it is too expensive and time consuming. You really need to have people that write code and are doing analysis. No. Well, the flip side of that is this thing, which is the kinesia one. There are several like these on the market now. You can PKG and whatnot. You can put it on one body part. Well, but why would you need that if the data that it's providing is actually incorrect? You need the amount of data in somebody getting up, standing, and walking. This is a complicated maneuver. And if you, yes, sure, we don't have targeted therapy for somebody that has left foot turning compared to the right arm. I understand that. But that doesn't mean that you should keep the technology at a dumb level of measurement. I disagree with this. And again, 10, 15 years ago, when we didn't have the bandwidth to be able to record large amounts of data, that may be fair, but not anymore today. And then there are these kinds of things, OptoTrack, which is another Vicon-like system, and Kinect, which have been in and out in terms of measurement. And there's a new thing that my friend, collaborator in Norway, Harris Sulius, and his group have been looking at, which is a wireless system, a Wi-Fi system. So you have a Wi-Fi network in the house broadcasting, and as the person navigates through that Wi-Fi network, it'll tell you, it'll break that. And just now Richard showed me a video-based system. But the problem with any of those things is that you have to physically record the video. Finally, you still have to bring it to the lab and record. You cannot take that home. You're not going to be, plus you're restricted often to one room. You're not able to actually have the data in somebody walking outside on the lawn. I mean, how are you going to get that? So you need a system that transmits wirelessly to a base or even a data logger, which allows you to do all of these things in that ecological environment. So for example, a measurement of all of these things. So we decided that, you know, technology is already out there. There is all kinds of sensor technology that allows you to measure whole body movement, especially in the animation world. Right? So this was 10 years ago, and you know these systems. There's both the synertial system and XSense. And Disney, the US military, all these people use these systems to be able to do high-end measurement of motion, hundreds of thousands of dollars. So long story short, we were using originally synertial system, and then now we've been using XSense, which is much better, and they allowed us access to their device, which gave us, so they didn't really do very much in terms of programming for us. They did nothing at all, except for giving us a raw signal. And then we've spent the last 4 or 5 years building something that is a lot of work, which is a biomechanical model of the individual, because there is no reference in this system now, which is very good. You can put on 2 sensors and allow the system to, so if you only want the right leg, you can just do the right leg. You don't need the whole body suit. Because there is no actual, it's reference to each other, right? And this is that system, and mandatory for fellows to pose with things on them. And so that's Dr. Aditya, who's now gone back to India. He was one of my fellows in movement disorders. 17 sensor system, each sensor, accelerometer, gyroscope, and magnetometer, so it's tuned to the Earth's magnetic field. 78 joints data, 69 segments, doesn't matter, because the computer can do anything. Right? It can analyze any of that data. And we've, over the last few years, analyzed all of it. So gait analysis, I'll show you the parameters, and again, you can just think of it as gait. You can do everything in gait analysis. We can do bradykinesia, dyskinesia, and tremor. Right? Can record all of these simultaneously in the patient using the same set of sensors. And the other interesting thing is that because of the biomechanical model, you can actually play the video back. Right? So this is in the person, real person. You can see there's a left foot turning, the reduced arm swing, and she doesn't look like this, and there's freezing. We're not asking her to do anything. There's a turn hesitation. You can see this is like playing a video. Right? You can do a UPDRS on her now, right? Except that you don't have hypomimia, but because we don't record facial expression, and then away she goes. And all of these features are extracted automatically, right, from that video. And if you think that there's something wrong, and you can even get a shadow if you like, which is a nice feature built in by SEMA. But yeah, and she's now walking. The right foot is turning in, and we'll turn around and so on. So this animation is fully done. Then you need that biomechanical model to build this multi-segment animation, right? And then there you go. So this person does not require a camera in the home. So we published the first. I'll show you very quickly bits and pieces of this. The video is a bit stretched because I had to fit it in that window. So this is the timed up and go task segmentation, and this person is walking. You can see reduced arm swing. They've got a bit of a truncal sway. All of this is animated using the biomechanical model, so it's real. It's not a Disney animation, right? So this is exactly how the person looks, and as they turn around, you can get all the measurements of tug. All been published. This stuff. So, and there she sits down. Okay, so this is what you would do with a tug task. That is what the raw signal actually looks like, and feature extraction can be done from that. I think my mouse will work on here. Yeah, there we go. So you can see that here are the segments of walking and extraction. I can't exactly see you on the screen, and this is too small for my old eyes now to look at this screen. So this is from right and left hip. So this is basically to show you what the raw signal looked like, nothing else. And from that, we have all of this: initial contact, heel strike, load response, heel off, opposite initial contact, toe off, all the things that are done on a gait carpet, which is expensive and it requires a lot of space. As you were saying, no space required. You can do this. Oh, you'll need space to walk around, but you could walk around like this as well, and you'll be able to record that. And so all of that is extractable, and we've shown that with standard methods, which is gait carpet, the correlation is very, very high. Here's freezing of gait detection. You'll see that this person has episodes of freezing of gait, and all of that can be extracted with the mathematics that has been done in the system, which we won't talk about. And then there's excellent correlation with visual. So we've done this with the gait carpet. We've also done with a clinician saying that, that's freezing, that's freezing, that's freezing, and the correlation is 90-95%, and that's assuming the clinician is right, and the pickup might be 100%. So close to 90-95% in most cases in gait freezing, in all of the gait features. And the SEMA is writing those 2 papers slower than I would like, but it's getting done hopefully in the new year with the final gait. The tug and bradykinesia, et cetera, all have been published, and here's the bradykinesia. What I was talking about before, and this is of course in journals that you would not normally clinically read, and what I was saying before, that instead of having tasks that are random, we do standardized tasks, which means that the person is sitting in a chair, even in home, right? So we haven't actually sent the suit home with the patient just for them, but we've gone to their home and done this in their home, especially because the original suits were $40,000, and so we didn't want to have them spill coffee on it. Now we can get them for 15, and we can easily probably get them for 5 if you buy a lot of them. And these patients do like Adi is doing there, very standardized set of tasks. This, that, foot tapping, sit to stand, and do it 3 times. And they can do it at whatever time you want, 9 o'clock, 10 o'clock in the morning, again at 1 o'clock and 4 o'clock, and keep doing them as long as you would like. Provides you all of this measure of tremor, bradykinesia, dyskinesia. Each is a separate analysis, but it's all packaged together in one box. So depending on which type of measurement that you want, you either do localized assessment for botulinum toxin injections, etc., or pump therapy, right? So here's bradykinesia. So this is the task that this person is doing, the patient moving that arm left and right. You can see that, again, you can rate this in the UPDRS. Maybe you rate this as 0 out of 4, right? And you can see that on either side. We don't do all of the little things like this because it's not necessary to be able to get the same level of validation just from doing one task. We can actually look at wrist rotation time, elbow rotation time, and shoulder rotation time all at the same time because the sensors are there. You don't need to do each movement. I initially wanted them to do this, but it sounded really dumb because you could get all from the 3 sensors that were there at the same time. And this is, again, the same kind of signal thing that I showed you before. You can see the variability of angular velocity between healthy and Parkinson disease patients. You can filter this. We've got different types of filters for tremor versus bradykinesia versus dyskinesia, depending on what the frequency bandwidth is. The neat thing is that you can then, this was the bradykinesia index that we had, you can plot them, and this was our DBS monitoring. So in a patient that you're programming, visit 0, 1, 2, 3, 4, 5. Different settings are available to what you've done in your programming, and you plot that over time as compared to just the UPDRS, which you can also do the same way, and say that, look, you know, there in visit number 4, the setting produced the best bradykinesia index because the lower the better in this. We've now corrected that just visually to say that, higher the bradykinesia index, closer to 100 is better. It doesn't matter. In this case, the lower is better, just like in the UPDRS. That's why we started with this like this, that at those settings, bradykinesia was minimal as compared to levodopa, and so we need to have the trajectory go to that. So that can be plotted for the physician, and we've done that with the whole body bradykinesia, sit to stand, walking, another paper that was published from those assessments. Large number of Parkinson patients. Here's a patient with tremor. This is using the, not the tremor tech system, because that's much more fidelity in that than in multiple joints. This is global tremor in the joints in this upper limb in the patient with Parkinson disease, comparing healthy versus, so it can record this, and we can then plot tremor analysis in groups of patients. So there's another project that we had done where we had patients early, mid-early, later, and late in their disease to look at what it looked like. You can see the trajectory off versus on, all bodysuit analysis, and the variability can be plotted in terms of tremor measurements in these people. For rest tremor, postural tremor, all with the same suit, so you don't have to change anything, right? So you're not changing the devices or technology. You put this on, and you can get them to do everything. It takes 10 minutes to do the entire task, or however long you want, and how many ever times you want. And the same thing is true for dyskinesia. And what I was saying before, in that video, you can see that that lady is doing a task on one side. There's tremor in the right upper extremity. The right leg is moving up. You can't do that with a single sensor because whether it's important or not, well, maybe it's not important, but it is important if you are trying to understand what's happening to the entire motor system. So again, we don't need to belabor this. The raw signals can be plotted like this. We don't show the raw signal to anybody. And when we did that in that same group of patients, you can see as the patients were in later stages of disease, dyskinesia severity worsened. This is all compared to the UDysRS in clinic. This is all automated recording from the bodysuit. So it provides you in the same patient a score. I showed you a different slide, but it'll give you a bradykinesia score, tremor score, dyskinesia score at one point in time, in each limb, in the whole body, all together at one time. And then you can plot that in this group. You can see that our UDysRS showed an increase, but in the bodysuit, the dyskinesia was substantially high as patients, and as you saw in that graph as well. All of this is, the above 2 lines are automatically detected. The one below is a clinical assessment. The trajectory is similar, but the dyskinesia reading in the clinician was lower, whereas the system detected a higher amount of dyskinesia than was visible to the clinician. Now, this is a problem. You might say that then it is not troublesome dyskinesia, it is not relevant dyskinesia, and that's true for all sensors. You may detect a tremor, which may not actually be clinically significant, and that's a decision that, based on your experience using, same as a clinical scale, what the semantics of that dyskinesia or tremor might mean. And then, of course, just a little GUI. We just put it together quickly for this couple of talks that we're doing here this week. It can present to you tremor, bradykinesia, dyskinesia, etc., all on different days. You just click through, it'll present that to you. This is real data from real patients as over time as these patients progress. Same thing, visit 1, 2, 3, 4, whether it's duodopa or clinic or whatnot. This can be provided to the, just like the tremor tech, over cloud. So the data is collected, 17 sensors uploaded, all of the analysis is done, and you get a little sheet which says bradykinesia indexed on Sunday, so and so, like your puffer thing that you were showing me with asthma. Same idea here. And all that the physician sees is a chart saying that over the last week, Sunday, Thursday, and Saturday, that's what happened during the day to this person's state, plotted for you, and from the home, so for home monitoring, right? And so allowing monitoring for long term. So this is just a bunch of GUIs. So in terms of how to use this data in optimizing current therapy, well, about 10 years ago, work was being done with a friend of mine, Romulo Fuentes and Miguel Nicolelis from now in Chile, looking at spinal cord stimulation in rodents. So both rat and primates showed that stimulation of the spinal cord was improving gait. So assorted number of cases in patients largely with pain syndromes in Parkinson disease. Gait had shown a total of about 30 cases around the planet had shown that maybe there's some improvement in gait in patients with Parkinson disease that were getting spinal cord stimulation. The mechanism of that we can talk about offline if people are interested. We spent quite a bit of time talking about it today. Long story short, we decided that since the primate work that had been done with Miguel and Romulo was so positive, heck, we had to try something in patients with Parkinson disease. So nobody was willing to do this. We happened to have a bunch of stimulators left from a government, because we publicly have funded system, gave us 40 stimulators for pain patients, and happened to be that in the end of 2 years, 3 years ago, at the end of that year, we were chatting about this, and Andy Parent, who's the chief of neurosurgery and does these functional things for us, said that, well, you know what, we've got 5 of them left over. You got to use them up. So otherwise, the government will say you only use 35. We will give you 35 the next year. So I said, okay, well, we're going to put them in. So we didn't tell anybody except the ethics people that we're going to do this, of course. We got through all that, and we put 5 of them in. And this is what has been a big success. So just to show you that success story.
This patient was barely able to walk for several years. Now take a look at the same man a few months later. He's had an electrical implant fitted to the back of his spine. Walking involves the brain sending instructions to the legs. Researchers believe that Parkinson's disease reduces the signals
Remember,
coming
this is
back,
media, so
causing the patient to freeze.
But it has a good summary, so
Boosts
that's
that
the video is
signal,
nice.
enabling the patient to walk.
They came to our lab.
Have a little bit of a picnic.
Gail Jardine,
You get to see London, Ontario
a
again.
few months ago. This is the first time she's walked with her husband Stan for more than 2 years.
Which is true.
Because she would freeze, she had frequent falls. Researchers monitor
Part of
her
my lab
progress
downstairs,
using sensors on her suit and socks.
I can walk better.
So we actually use the outputs from the suit to optimize the space within which all of the parameters of gait had to be optimized. So stride length, stride width, velocity, double stance, single stance, etc., plotted what the normal looked like, and the programming that was done to see, okay, did we increase that, did we reduce that? So programmed. There's Olivia Samotis, who's doing her PhD in this. One of those people who's got a CV with 30 papers already in there in movement disorders and class 1 and whatnot, etc. Very smart girl. And this is the quantitative EEG that we've done in these patients. That's Pallab Ghosh from London, here, London. That come to the lab and that produce this thing. But it shows you a variety of different things that we're doing, which actually shows quantitative EEG change in these patients after spinal cord stimulation, right? And anyway, so so he's also So the next trial is 15, right? So that's good enough. I mean, that's it. So the idea behind this is that those first 5 patients had such dramatic improvement at 6 months. We now have 3-year data, which is Olivia just finishing writing up, to show that still at 3 years, these patients haven't progressed in their gait, right? And so it's not as good as it was at 6 months in terms of all of the features, but the one feature that stands out remarkably is the number of freezing episodes, right? So you can see that even at 3 years, this is now a little over 3 years, these people are not freezing, to the point that I've tried to convince some of these people to turn the thing off, right? So turn it off and come a week later and see what's happening. They're unwilling to turn it off because at the most 48 hours. And again, I asked the ethics people, and they wouldn't allow us to put this through to tell these people to turn it off because fall risk is so high. And some of these people, like Gail in that video, said now at almost a year with her, which is the second bunch of people that we've done, she's had 1 fall, and before that she was falling 3-4 times a day, right? Maybe it's a placebo effect, but I can't make her fall if I turn the thing off. So I haven't turned any of them off for longer than 48 hours. The interesting thing though, Richard, is that if I turn them off for 48 hours, they still have benefit. So it's not that their freezing returns to baseline, like you see in tremor and Parkinson disease. You turn off the DBS and the tremor comes back. It doesn't seem to happen. So I truly believe that there is some fundamental change going on, and I wouldn't call it sensory. We discussed this morning at length. It is simply an input-related drive within the network. And at 3 years, if these people are still wanting to use the device. However, if you look again at that spider plot of all the things that, again, this is not a computational way of doing this, is simply iterative. We turn the thing on, measure, say, what does it look like? Okay, that's not going to measure. So it is time intensive. My hope is that as we do more, this will be something that will be an optimization function we just build. But the freezing of gait, a number of freezing of gait episodes, and fog time and duration, all of these things remain in these patients. So getting to the last part of what I wanted to say, because running out of time a little bit, is the whole concept of being able to take all of our technology and the expertise that we have, whether it's kinematics, whether it's measurement of tremor and optimizing botulinum toxin, to the community, because the technology is simple enough that somebody that is not particularly savvy in having to write anything will be able to do the recordings for you or for us. You can imagine, like the kit that Richard showed me in his lab. You have a box, you've got a bodysuit, you've got a tremor tech device, etc. Somebody goes to the person's home, they do the analysis in the person's home. 2-3 days, a healthcare support worker, doesn't have to be anybody that has engineering background, does the recording locally, brings back that data for you through cloud, and the physician has availability of saying, okay, I changed levodopa from this, I changed the DBS setting. The whole idea is to be able to program these people in their own environment based on what they're doing. And this could be other markers, such as quantitative EEG. Being north of our great nation below, I had to use the term that Mr. Trump uses, to making QEEG great again, like making America great again, whatever that means. But certainly the idea of having network measurement as being a way of doing this. We have a 32-channel EEG. We've developed this new analysis technique over the last little while, along with the usual techniques of something called dynamic cross-entropy that's been published. And the construct behind it is that in addition to measurement of the kinematics, can we have another biological measure of what's happening within the network? So an EEG cap is easy these days, not that expensive, especially the lower number of channels. Along with this, EEG cap is put on, recorded simultaneously as people are doing the other assessments. You now have a clinical measure, a kinematic measure, and then you have a physiological measure of what the state of that system is. It's not ready yet in the sense of what we want to do, but is it possible for us to understand this a bit better? Because all of these things are portable technologies, and I think that we definitely need to employ them. You're already doing it to some extent, sending these things to patients' homes. This is required along with the measurement of their physical state space. The other thing that you could measure in this, and we've actually done this in depression, in traumatic brain injury, right? So Dorian, who's one of my research scientists, was my postdoc 10 years ago, and then he went to Stanford and Vancouver, et cetera. He's come back to the lab now as a senior scientist in my lab. And he's done extensive recordings in patients with mood disorders, with schizophrenia, using this quantitative EEG technique. And those papers we are writing right now, large numbers. It's part of a cohort of psychiatry patients in Canada that he's collected this data. The final idea behind this is, can you provide therapy locally, like botulinum toxin, which requires, that's why I said about the golden hands kind of thing, a lot of experience before you get good. Ad hoc, for sure, but at the same time, it does work. But I can't teach that to anybody. Can you provide, using that kinematic data, that expertise by saying, physician, inject that muscle? Because that's easy to teach. How to assess that patient is very hard to teach. So the idea behind this is, if a local injector, a physiatrist in Chatham, Ontario, is willing to do the injections but can't do the assessments, well, the assessment is done for you by the machine. And all you've got to learn, and most of these people know the anatomy very well, is which muscles to inject under whatever technology that they want to use, EMG or just needle or ultrasound or both. But you can't do the former. The same thing is true with treatment of the electrophysiology. Is it possible for us, and I'm a big skeptic of this, as we were saying, can we deliver charge using transcranial stimulation? And Richard and one of his colleagues is looking at transcutaneous stimulation, the spinal cord. Again, I'm not a believer of whether you're going to be able to deliver enough charge through these structures like this to be able to get sustained benefit, like RTMS. Doesn't work for any duration of time, but it is certainly intriguing that if we could somehow get a physical state and a mental state of the network, so to say, in a way, using quantitative EEG, the state of the network electrophysiologically, and then consider tailoring our treatment, whether it's spinal cord stim, for brain networks, or transcranial stimulation for premotor, motor cortex, cerebellum, doesn't matter, for treatment of ataxia, etc. Is it possible for us to bring this therapy also at home? So we're doing all of these pilot studies right now. In Parkinson disease, we've got a 100-patient cohort of on-off PD medications, different state, on-off, DBS, etc. Huntington disease, we've just begun with dystonia and ataxia. We haven't done Huntington, but we have traumatic brain injury as well, and then apply this non-invasive stimulation. All of you here are aware of this non-invasive stimulation thing, and I say I remain significantly skeptical about these things. TDCS, which is DC current, which is basically an expensive battery that is used to put the voltage across, and TACS, I saw a wonderful poster for tremor in Richard's office, which basically didn't work, but and I would think that that's what my thought would be. But then a new technique or technology that has been developed, which is TPCS, and there is a commercially available device which is very rigid, and it's FDA approved, by the way, for TPCS for depression. But we've built one in our lab that allows us to program each of those subcomponents of the pulse current stimulation. So the idea is, using quantitative EEG, localize areas of network dysfunction which correlate to the physical state, and then provide electrical stimulation either through spinal cord if it's for gait, or through transcranial stimulation to apply to the network. Still rudimentary, still in its primitive stages, but potential is there, even though I keep saying I remain skeptical, whether you're going to stimulate cortex and spinal cord, cerebellum and spinal cord, et cetera, et cetera. There are people that are involved and interested in doing this. There's a couple of papers with that. And so really, the idea behind, there's one more other thing that we've done that I wanted to briefly mention, because that paper also just got accepted in Nature Scientific Reports last week. And so the idea here, we talked about at dinner yesterday, is to understand what is the phenotype of this network outside of the physical state that we're measuring. Is it possible for us to understand the dynamic of this network? So Matthew Bernardaire is one of our biomechanical engineering master's student, did this work over the last 2.5 years. And what he looked at is how patients with Parkinson's disease see space and time. Sounds very fancy, but it is exactly that. How patients envision a space. So all of us now, I mean, for me, even with this 1 hour, I can go out and tell you approximately the length and width and the diagonal of this hall, how many approximate seats there are. I have a spatial model maybe it's in my hippocampus, I'm not sure exactly where it might be, but it is there to represent what people call place, right? So location. However, in patients with Parkinson's disease, the thought is that the hypothesis has been for a long time is that this is misrepresented. If I actually see that this coffee is not 2.5 feet away, but 2 inches away, then I'm going to make a movement that is quite conducive to that spatial representation, not doing that. Right? So can we explore this? And that's what we did in this study. We looked at how patients with Parkinson's disease, without actually having to make a movement, interpret space. So if there's a big ball, there are multiple tests in here, but just one example. There's a big yellow ball and a small yellow ball, and the normal psychophysical state would be the big ball will fall faster than the smaller ball. And we tell them that you got to tell us which ball is falling faster, and we actually make the yellow ball, it's a smaller ball, fall faster. Right? What is, or maybe do it the correct way that you've told them. What is the discriminatory power? What distance are they able to tell that, yes, this is moving faster, at what velocity differences, etc.? And there was a significant difference in patients with Parkinson's disease in space and time, etc. When that paper comes out, the details are all in that first paper. There are 2 more after this. This one is on time, the second one is on space, and the third one is putting it together as a spatial-temporal mismatch. And the idea of putting it together is that the network that we have recorded is misrepresenting time and space, which potentially through transcranial stimulation or otherwise, spinal stimulation or oral medicine neurochemistry, is topologically changing that map. And in this paper, we've shown how levodopa does it and how DBS does it differently in terms of how that spatial map gets reoriented. So last slide. The idea behind this is to provide a home-based assessment tool potentially. Any home care worker can use them, whether it's EEG along with kinematic sensor, also autonomic sensory recording with this blood pressure, heart rate, nocturnal data monitoring. It should be QEEG, not EEG, at home. This package now provides you with a phenotype, and I think what Richard was saying is also extremely interesting. With a tablet, let's say this task that Matthew has done, they can do this at home while they've got this going on in their recording. Now you've got a state package of this individual, whether it's an old person, Parkinson's disease, doesn't matter, traumatic brain injury, somebody that has had concussion. The idea would be that you've brought this expertise at home. It is agnostic to the patient's ability to fill out diaries, which are usually done sitting outside the waiting room while having coffee, or whatever they can remember in terms of their state, et cetera, et cetera. This is agnostic. It's agnostic also to the expertise of the individual doing the procedure, because it's all done, as long as it's done in the proper way. If they decide not to stand at all, then, well, sure. It's like we were talking about medication. If you decide not to actually open the box but don't put the pill in your mouth, well, then there's some other problems there then, right? And so that's the construct with this tech that I wanted to get across and show you how some of these things we've done in terms of spinal cord stimulation and Botox treatment. So I'll stop there. Sorry, I went on a little bit, but thank you very much.